What if the universe itself was born from a journey through time? What if the very first act of creation wasn't just a moment of expansion, but an event that twisted the fabric of reality so profoundly that time itself became a traveler? We're about to explore one of the most astonishing possibilities in all of physics. That time travel isn't something humanity might invent centuries from now, but something that already happened at the very dawn of existence. Imagine looking back at the birth of our cosmos and realizing that what we thought was a simple beginning might actually have been the universe's first incredible journey through time itself. This isn't just wild speculation. Some of the brightest minds in theoretical physics are proposing that time travel might be woven into the fundamental nature of reality. The implications are staggering. If time travel occurred at the universe's creation, it could explain mysteries that have puzzled scientists for decades, from the precise fine-tuning of physical constants to the mysterious arrow of time. It suggests that our entire existence might be built upon a foundation where past, present, and future are not separate chapters but interconnected moments in a cosmic story that began with the ultimate temporal paradox. Today, we're embarking on an extraordinary exploration of 30 compelling theories about the universe's first time travel event. We'll journey through concepts that challenge everything we thought we knew about reality, from quantum gravity and closed time-like curves to multiverse theories and cosmic inflation. Each theory offers a unique window into how time itself might have operated in those first unimaginable moments, and how those primordial events continue to shape our reality today. This is more than just physics. It's a story about the very nature of existence, and it's a journey that will change how you perceive time, space, and your place in the cosmos. Our first theory takes us to the very edge of comprehension, proposing that the origin of everything we know was not a beginning in the traditional sense, but a moment where time folded back onto itself. This is the concept of the Big Bang time loop. Instead of a linear progression from a singular point, imagine the Big Bang as the cosmic equivalent of a snake eating its own tail, a closed loop where the effect and the cause are one and the same. In this model, the universe's own eventual collapse, perhaps in a big crunch, doesn't just end everything. It becomes the very same compressed state of infinite density that then triggers the next Big Bang. The end literally becomes the new beginning, creating a cycle of death and rebirth on a scale so vast it defies our everyday understanding of time. This idea emerges from the strange world of general relativity, where Einstein's equations allow for the theoretical existence of closed time-like curves, paths through spacetime that loop back on themselves. If such a curve were applied to the entire cosmos, it would mean our universe's timeline is not a straight line with a start and finish, but a circle. There is no true before the Big Bang because that moment is causally connected to its own future. The moment of creation is both the first event and the last event, locked in an eternal dance. This elegantly sidesteps one of cosmology's most perplexing questions: what caused the Big Bang? In this model, the universe is its own cause, an ultimate bootstrap paradox where it created itself. The implications of a circular timeline are profound. It suggests that the laws of physics and the precise constants that allow for our existence might not be arbitrary. They could be finely tuned through countless previous cycles, each iteration subtly shaping the next. The universe we inhabit might be the latest version in an infinite series, refined over eternal repetition. This introduces a fascinating possibility. The faint echoes of previous cycles might somehow be imprinted on our own, perhaps hidden within the cosmic microwave background radiation waiting to be discovered. It transforms the universe from a one-time event into an eternal, cyclical process, offering a breathtaking new perspective on our place within the grand, possibly endless flow of time. But if the entire cosmos is caught in a grand, cyclical loop, what was happening on the smallest possible scale at the very instant of creation? To peer into that first fleeting moment, we must shrink our perspective down to an almost unimaginable size and consider our second theory, the quantum gravity time jump. While the first theory dealt with the universe's overall timeline, this one ventures into the bizarre quantum realm that governed existence in the first fraction of a second. Picture the universe not even a second old, but a mere 10 to the power of negative 43 seconds old, a duration so short it has no meaning in our human experience. This is the Planck epoch, a period where the density and temperature of the entire cosmos were so extreme that the very laws of physics as we know them did not yet exist. Gravity, which normally shapes planets and galaxies, was not a smooth force but a seething, roiling quantum field, fluctuating wildly. In this frenzied environment, the distinction between past and future may have been just as fluid. The extreme energies could have warped the fabric of spacetime so violently that it created temporary, microscopic tunnels, not for spaceships but for fundamental particles. Think of it as a bubbling quantum foam, a frothing sea of virtual particles popping in and out of existence, as the universe itself does at this scale. Within this foam, the conditions might have been just right for particles to briefly tunnel not through space but through time. A single particle could have momentarily jumped backward, interacting with its own past self before snapping back into the forward flow of time. These wouldn't be the dramatic time machines of science fiction, but fleeting, probabilistic hiccups in the chronological order of the cosmos. The potential consequences of these tiny temporal jumps are anything but small. Every interaction in the quantum foam could have served as a random number generator for the universe's settings. The specific ways in which particles interacted with their past or future selves might have directly influenced the values of the fundamental constant, like the strength of gravity or the charge of an electron that we observe today. It's a compelling explanation for the mysterious fine-tuning of the universe. Perhaps the constants aren't perfectly set by design, but were effectively randomized and locked in place during this turbulent period of quantum time travel. The very fabric of our reality, the rules that allow atoms and eventually us to form, could be the frozen echo of countless microscopic journeys through time, a permanent record of the universe's first and most chaotic temporal experiments. Yet the extreme physics of inflation might have woven something even stranger into the very fabric of the cosmos, natural, primordial corridors for time travel. As spacetime expanded at speeds beyond comprehension, the fabric of reality wouldn't have stretched smoothly like a simple sheet of rubber. Instead, this violent and exponential growth could have created immense tensions and topological defects in the structure of spacetime itself. Picture it like rapidly freezing water. The process happens so fast that bubbles and fissures get trapped within the ice. In the same way, the inflationary expansion might have frozen into existence a network of cosmic strings infinitely long, incredibly thin filaments of pure energy and stable wormholes threading through the newborn universe. These wouldn't be the carefully constructed tunnels of science fiction, but natural formations much like canyons and rivers are natural features of a landscape. Theorists propose that some of these wormholes could have been special, connecting not just two distant points in space, but two different points in time. In the seething energy of the inflationary field, the distinction between space and time was likely blurred. A wormhole forming under those conditions might not just create a shortcut across the galaxy, but a bridge to the past or the future. Information in the form of quantum fluctuations or even fundamental particles could have briefly flowed through these temporal corridors, meaning the universe was communicating with its own different ages at the very moment of its creation. The most fascinating part is that these ancient time tunnels might still be out there. While many would have collapsed or evaporated as the universe cooled, the most stable ones, perhaps stabilized by exotic matter or wrapped around cosmic strings, could have survived for billions of years. They would now be fossil relics of the universe's most violent growth spurt, hidden in plain sight. We might detect them indirectly through their gravitational influence or by spotting strange, inexplicable patterns in the cosmic microwave background anomalies that look like echoes from another time. If they do exist, they are not just fossils, they are a permanent part of the universe's architecture, a built-in network of temporal pathways waiting to be discovered, offering a silent testament to the idea that time travel was not an anomaly, but a fundamental feature of the cosmos at its birth. Now, let's consider the idea that the universe's first time traveler wasn't a person or even a particle, but a flaw in the very fabric of reality itself. This brings us to cosmic strings, which are perhaps one of the most exotic and fascinating predictions of theoretical physics. Imagine the universe in its first moments, cooling from an indescribable heat. As it cooled, its fundamental fields underwent phase transitions, much like water freezing into ice. And just as ice can form with cracks and fissures, the fabric of space-time might have frozen with topological defects, immense, stable structures woven into the cosmos. The most extreme of these are cosmic strings, hypothetical entities that are thinner than a proton but so dense that a single inch of one could weigh more than a mountain range. They are essentially cracks in space-time, and their gravitational influence is almost beyond belief. A cosmic string's immense mass warps the space around it so severely that it doesn't just create a gravitational well like a planet or a star, it creates a unique kind of curvature. The space around a straight cosmic string is actually conical. If you were to travel in a perfect circle around one, you would find that your journey covers less than 360 degrees. This bizarre geometry has a startling consequence for time. According to Einstein's theory of general relativity, gravity doesn't just bend space, it also bends time. The incredible gravitational pull of a cosmic string would warp the dimension of time just as severely as it warps the 3 dimensions of space. If 2 of these strings were to form in the early universe and then move past each other at incredibly high speeds, their combined gravitational fields could twist space-time into a closed time-like curve, a literal loop in time. This means that in the tumultuous environment just after the Big Bang, the conditions might have been perfect for these natural time machines to spontaneously form. A particle or a ripple of energy following a path around these 2 moving cosmic strings could find itself not just in a different location, but in a different time. It wouldn't require a machine or any technology. It would simply be a consequence of the universe's own dramatic birth pangs. The first instance of time travel might not have been a deliberate act, but a natural gravitational phenomenon. An object or piece of information taking a shortcut through time because the geometry of the newborn cosmos permitted it. The legacy of these strings could be far more than a one-time event. While many might have decayed or annihilated each other, some theorists suggest that a network of these cosmic strings could still stretch across the entire universe today, like the cracks in a vast cosmic pane of glass. If they exist, they are fossil relics from the first moments of time, and they might still be capable of creating these temporal loops. Finding evidence for cosmic strings would not only confirm a profound prediction about the origin of the universe, but would also provide a tangible mechanism for time travel that was built into the cosmos from its very beginning. It suggests that the potential for journeying through time isn't something we need to invent, but something we might one day discover, hidden in the gravitational folds of these ancient cosmic scars. While cosmic strings offer a compelling mechanism for early time travel, they are not the only ultra-dense objects that could have warped time in the infant cosmos. To find another potential candidate, we must look to the darkest and most mysterious entities known to physics, black holes, but not the stellar mass black holes formed from dying stars or the supermassive ones anchoring galaxies. We must look for something even more ancient and primordial. This leads us to our 5th theory, that the very first black holes might have served as the universe's original time portals. The standard model of cosmology tells us that the first generations of black holes formed long after the Big Bang from the collapse of the first massive stars. However, an intriguing alternative suggests that some black holes could have been born in the universe's opening seconds. In the incredibly dense and hot soup of the primordial cosmos, random fluctuations in density might have been so intense that regions of space simply collapsed under their own weight, forming black holes directly from the energy of the Big Bang itself. These wouldn't require stars. They are thought to be purely gravitational artifacts of the universe's violent birth. Ranging in mass from smaller than an atom to larger than a star, these primordial black holes could have been incredibly numerous, littering the newborn cosmos like gravitational landmines. The environment inside a black hole, especially one born from such extreme conditions, is where the laws of physics as we know them break down. At the very center lies the singularity, a point of infinite density where space and time cease to have any meaningful definition. According to some solutions to Einstein's field equations, particularly those for rotating Kerr black holes, the singularity isn't a point but a ring. And this ring-shaped singularity presents a fascinating possibility. The mathematics suggests that if something could pass through the ring without being destroyed, it wouldn't just emerge in a different part of space, it could emerge in a different part of time. The immense rotational energy and gravity of the black hole would twist spacetime into a closed time-like curve, a pathway that loops back on itself. Now imagine the early universe still seething with energy and rapidly expanding. A particle or a packet of energy falling into one of these newly formed primordial black holes might not have been simply crushed into oblivion. If the conditions were just right, if the black hole was spinning at a specific rate and had the perfect mass, that particle could have been hurled through the ring singularity and out through a hypothetical white hole, emerging not at another location, but at an earlier or later moment in the still unfolding history of the cosmos. It wouldn't be a journey a human could survive, but for information or fundamental particles, it might have been a possibility. The first instance of time travel could have been an entirely natural gravitational process, with the universe using its own most extreme objects as temporal gateways. The implications of this are profound. If even a tiny amount of information from the future could have leaked back into the past through these mechanisms, it could have acted as a subtle feedback loop, influencing the initial conditions of the universe itself. This offers a potential, albeit wild, explanation for the phenomenon of fine-tuning. The physical constants and laws we observe might be so perfectly set for life because they were, in a sense, calibrated by information that traveled back from a future where life was possible. It turns the universe into a self-regulating system where cause and effect are not a one-way street but an intricate, timeless loop, with primordial black holes serving as the crucial junctions in this cosmic network of time. While black holes present a gravitational path to the past, another possibility emerges from the quantum realm that is even more counterintuitive and perhaps more fundamental. This theory suggests that the universe's first time travel didn't require massive objects or cosmic strings, but was woven into the very fabric of quantum connection itself. We now turn to the bizarre phenomenon of quantum entanglement and its potential to link not just particles across space, but perhaps across time as well. Quantum entanglement is often called spooky action at a distance for a reason. When two particles become entangled, they share a single, unified quantum state. No matter how far apart they are separated across a room or across the galaxy, measuring the property of one particle, like its spin, will instantaneously determine the property of the other. This connection seems to defy the universal speed limit set by light, operating faster than any signal could possibly travel between them. For decades, physicists have grappled with this mystery, but a growing number of theorists are asking a more radical question. If this link can ignore the constraints of space, could it also transcend the flow of time? Imagine the universe in its first fleeting moments, a superheated plasma of energy where particles were being born and entangled in a chaotic quantum dance. In this dense primordial soup, the distinction between here and there was nearly meaningless, and the distinction between now and then might have been just as fluid. Some interpretations of quantum mechanics suggest that an entangled pair doesn't just share a state across space, they share a state across their entire timeline. Measuring one particle in the present could be seen as influencing not just its partner's present state, but its past state as well. In the infant universe, this could have meant that information was effectively leaping backward or forward in time along these quantum threads, creating a web of instantaneous communication that bound different moments of the cosmos together. This isn't about sending a human or even a complex molecule back in time. It's about the transfer of pure information, the most basic building block of reality. In those first instants, the universe was essentially programming itself, setting the values for the fundamental constants and laws that would govern everything to come. If entangled particles were able to exchange information across time, they could have acted as a form of cosmic feedback loop. A fluctuation happening at one moment could send a signal back to an earlier moment, subtly adjusting the probabilities and outcomes of quantum events. This process could have fine-tuned the early universe, creating the precise conditions necessary for complexity and life to later emerge. The spookiness of quantum mechanics might not be a bug but a feature. The universe's built-in mechanism for ensuring its own stability and coherence by allowing its future to gently guide its past. The implications of this are staggering. It suggests that time, at its most fundamental level, may not be the linear, one-way street we experience. Instead, the quantum world might operate with a kind of temporal democracy, where past, present, and future are all equally real and can interact with one another. The universe's first act of time travel wouldn't have been a dramatic journey, but a quiet, constant hum of information exchange happening everywhere at once, a foundational process as essential to the cosmos as gravity or electromagnetism. Finding conclusive evidence for this would revolutionize our understanding of reality, revealing that the arrow of time is not a fundamental law but an emergent property, a large-scale illusion born from a deeper timeless reality where every moment is eternally connected. Now we shift our focus from the quantum and gravitational to a force that is both pervasive and profoundly mysterious, one that dominates our universe's present and future: dark energy. This enigmatic pressure, making up about 68% of the cosmos, is the driving force behind the accelerating expansion of the universe. But what if its influence isn't confined to stretching the fabric of space? What if dark energy also holds a unique power over time itself? This theory proposes that the emergence of dark energy in the early cosmos didn't just push galaxies apart, it may have created the very first ripples and distortions in the river of time. To understand this, we need to revisit one of Einstein's greatest insights from general relativity: that space and time are interwoven into a single entity called spacetime. We're used to thinking of gravity as the sole force that warps this fabric, bending starlight and slowing clocks. But if a force can warp space, it stands to reason it could also warp time. Dark energy is that force. Unlike gravity, which pulls matter together and slows the cosmic clock, dark energy exerts a repulsive pressure, pushing spacetime apart. This accelerating expansion could have a direct and counterintuitive effect on the dimension of time. In regions where dark energy dominates, the relentless stretching of space might cause time itself to thin out, to flow at a subtly different rate compared to areas where matter still holds sway. In the simplest terms, the vacuum of empty space energized by this dark force could become a landscape of varying temporal speeds. Imagine the universe in its adolescence, a few billion years after the Big Bang. The initial fireball has cooled, galaxies have formed, but matter is still densely packed in a cosmic web. Then, dark energy begins to awaken and assert its dominance. As it does, it doesn't just create more space between galaxy clusters. It begins to alter the very tempo of time within those vast, growing voids. A clock placed in the heart of one of these immense cosmic deserts would tick ever so slightly faster than a clock within a dense galaxy cluster. This is a gravitational time dilation effect, but with a dark energy twist. The repulsive push of the vacuum energy effectively reduces the gravitational potential, allowing time to speed up. The universe isn't just expanding, it's developing temporal topography, hills and valleys of faster and slower time. This leads to a staggering possibility for the universe's first time travel. In the earliest epochs, even before dark energy became dominant, there would have been tiny fluctuations in its energy field. These random pockets of slightly stronger or weaker repulsive force could have created microscopic regions of extreme time dilation. In a zone of hyper-accelerated time, a billionth of a second inside the bubble could equate to a full second outside of it. For a fundamental particle caught in such a bubble, it would effectively leap forward into the future of the surrounding universe. Conversely, a region of severely slowed time would act as a trap, a pocket where the flow of time nearly stops relative to the outside, potentially preserving information from the very dawn of creation like a fossil in amber. These temporal anomalies wouldn't be tunnels or portals in the traditional sense, but more like bubbles of divergent time, popping in and out of existence in the quantum foam of the early universe. Particles or quantum information could have become isolated in these bubbles, experiencing a different flow of time before reintegrating with the rest of the cosmos. This means the first time travelers might not have moved backward or forward along a path, but were simply passengers on isolated rafts of time, drifting at their own pace on the cosmic river before reuniting with the main current. The legacy of this process might be written in the large-scale structure of the universe we see today. The vast voids and dense filaments of the cosmic web could correspond to faint patterns of different temporal flow, a permanent imprint of dark energy's first temporal push on the architecture of reality. So far, we've explored how time travel might have been woven into our own universe's fabric through loops, quantum jumps, and gravitational warps. But what if the very first journey through time wasn't a journey within our cosmos at all, but a journey to it from somewhere else entirely? This theory pushes the boundaries of the multiverse concept, suggesting that our universe's birth was itself an act of temporal migration, a branching off from a parent reality that created a bridge not just between spaces but between times. The idea of a multiverse isn't a single theory but a family of ideas emerging from cosmology and quantum mechanics. In one prominent version, known as the inflationary multiverse, our universe is just one bubble in a vast, eternal cosmic foam. The vacuum of this greater multiverse is seething with energy, and random quantum fluctuations can trigger the spontaneous birth of new universes through a process called quantum tunneling. Normally, we think of quantum tunneling as a particle slipping through an energy barrier it shouldn't be able to cross. Now, scale that idea up to a cosmic level. Instead of an electron, it's an entire universe, a bubble of new space-time tunneling out of the vacuum of a pre-existing universe. This is where the concept of time travel enters the picture in a profound way. When our universe tunneled into existence, it didn't just create new space, it created its own new timeline. The moment of our Big Bang could be seen as the point where our cosmic clock started ticking. But from the perspective of the parent universe, this event might not be a beginning so much as a branching point, a new timeline splitting off from its own. If any information, any quantum fluctuation or property was transferred during this tunneling process, it would represent information crossing from one timeline into another. That information wouldn't just be moving between universes, it would effectively be traveling into its own past, because the new universe's timeline begins at a point that, from the parent's view, is in its future. The birth of our cosmos could have been the multiverse's first instance of time travel. This leads to an even more mind-bending possibility, the fine-tuning of our universe. The physical constants and laws that seem perfectly calibrated for life have long puzzled scientists. the multiverse time bridge offers a potential explanation. Perhaps our universe isn't randomly tuned. Instead, the information that tunneled through from the parent universe wasn't random noise. It could have been a specific, stable configuration of laws, a set of instructions that ensured the new universe would be viable. In this scenario, the first time travel was a causal loop across realities, a future, stable universe sending the blueprint for its own existence back to its moment of creation. Our universe's laws are life-friendly because, in a sense, they were inherited from a reality that already knew they would work. The evidence for this incredible idea might be hidden in the oldest light we can see, the cosmic microwave background. This faint afterglow of the Big Bang is a snapshot of the infant universe. If our cosmos was born from a quantum tunneling event from another reality, the collision or interaction between the two space-time bubbles could have left an imprint, a strange, unexplained cold spot, or a specific pattern of polarization in the background radiation that defies standard inflationary models. While no such definitive evidence has been found, the search for these cosmic fingerprints continues. If discovered, it would suggest that we are not alone in the grand scheme of existence, and that our very beginning was an act of connection, a temporal handshake from a parent universe that set us on our course through time. We've journeyed through cosmic loops and quantum tunnels, but perhaps the most profound gateway to the past lies not in the stars but within ourselves. This theory ventures into the deepest intersection of physics and philosophy, proposing that time as we experience it is not a fundamental feature of the universe, but a construction of the mind. It suggests that the universe's first true act of time travel wasn't a physical event at all, but the emergence of consciousness which reached back and effectively created a past by the very act of observing it. To grasp this, we need to consider one of the most enduring puzzles in quantum mechanics, the measurement problem. In the quantum world, particles don't exist in a single, definite state until they are measured or observed. Before that moment, they exist in a blur of all possible states, a superposition. The classic example is Schrödinger's cat, which is both alive and dead until someone opens the box. The act of looking somehow forces all those possibilities to collapse into one concrete reality. This raises a profound question: what counts as an observer? Is it a machine, a human, or is it something about consciousness itself? Some interpretations, like the participatory anthropic principle proposed by physicist John Archibald Wheeler, take this a step further. They suggest that observers are necessary to bring the universe into definite existence. In this view, the universe is a vast, potentiality-filled system waiting for a conscious mind to give it form, to solidify maybe into reality. Now extend this idea to the dimension of time. If observation defines reality in the present, could it also define the past? The universe has been around for nearly 14 billion years, but for the vast majority of that history, there were no conscious beings to witness it. So what was the state of reality before we came along? This theory proposes that the past, just like a quantum particle, was not fixed. It was a haze of possibilities, a superposition of every potential history that could have led to this present moment. The first conscious observers, whether they were early humans or some other form of sentient life, didn't just discover history, they created it. By looking back through the evidence left in fossils, starlight, and cosmic background radiation, our consciousness performed a measurement on the past. Our inquiry forced the fuzzy probabilities of what might have been to collapse into the single, seemingly linear timeline we now call history. We are not just studying the past, we are finalizing it. This turns the concept of time travel completely on its head. The first journey through time wasn't a physical voyage, but a mental one, when the first conscious mind wondered what came before and began to piece together clues from its environment. It was effectively reaching back across billions of years and selecting one consistent timeline from a sea of options. Our collective observation continues to perform this function, solidifying a shared past. This implies that time is not a river flowing independently of us. It is a story we are actively telling, and in the telling, making real. The arrow of time, the relentless march from past to present to future, may be a product of our conscious perception, a necessary framework for making sense of the world rather than a fundamental law of physics. The universe's first and most ongoing time traveler is the conscious mind itself, forever looking backward and, in doing so, building the very road it walks upon. As we peel back the layers of the cosmos to its absolute beginning, we arrive at a period so brief and so extreme that it strains the very limits of physics itself. This is the Planck epoch, the first 10 to the negative 43 seconds of existence, a time span so short that it has no equivalent in human experience. To even speak of this duration, we must abandon our watches and calendars and enter a realm where time itself becomes a quantum variable, fluctuating and uncertain. In this unimaginably hot and dense state, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were unified into a single superforce. The energy was so intense that particles and antiparticles spontaneously blinked into and out of existence, and the very concepts of space and time as continuous, smooth fabrics break down entirely, replaced by a seething, probabilistic foam. It is within this chaotic, foundational froth that a radical hypothesis takes shape, the idea that the arrow of time did not yet exist. In our everyday world, time has a clear and irreversible direction. Eggs scramble but never unscramble, memories are made but not unmade. This is a consequence of increasing entropy, a law of thermodynamics that seems fundamental to our reality. But during the Planck epoch, the conditions were so extreme that the conventional laws of thermodynamics may not have been in effect. At these energies, the microscopic laws of physics, which are fundamentally time-symmetric, reigned supreme. For a particle interacting in this quantum foam, there may have been no inherent difference between moving forward and moving backward in time. A particle's journey was not a one-way street but a two-way path. It could just as easily travel backward along its own world line as forward, effectively existing in a state of temporal superposition. This primordial state of perfect time symmetry couldn't last. As the universe expanded and cooled at an incredible rate, it underwent a series of phase transitions, much like steam condensing into water. The first and most significant of these was the moment gravity decoupled from the other forces, breaking the perfect symmetry of the superforce. This decoupling is theorized to have locked in the direction of time. Think of it like a massive die being cast. The specific way in which the universe cooled and the field separated introduced a fundamental bias, a preferred direction for cause and effect. The processes that followed, like the formation of matter and the eventual onset of entropy, all flowed from this initial breaking of temporal symmetry. The arrow of time we experience today, with its relentless forward march, may be nothing more than a frozen accident, a relic of how the universe happened to cool some 13.8 billion years ago. The evidence for this profound idea might be hidden in the most subtle details of the particle world. Physicists carefully study the behavior of neutral K and B mesons, subatomic particles that exhibit a tiny but measurable difference in how they decay versus how their antimatter counterparts decay. This phenomenon, known as CP violation, is a direct demonstration of a fundamental asymmetry in time at the quantum level. It's as if we are seeing a faint echo of that first moment when the universe chose a direction. These microscopic asymmetries, amplified over the entire cosmos during the Big Bang, could be the very reason we have a universe dominated by matter instead of antimatter, and a timeline that only moves forward. The universe's first and most significant time travel event, therefore, might not have been a journey but a choice, the spontaneous selection of a temporal direction that made our structured, causal reality possible. But if the universe's initial state was a perfect symmetry, how did anything ever happen at all? how did we get from a featureless, timeless quantum foam to the structured cosmos we see today? The answer might lie in the universe's inherent restlessness, a constant fizzing and bubbling at the smallest scales that provided the raw material for all of creation. This brings us to a theory that connects the ghostly world of quantum mechanics directly to the large-scale architecture of the cosmos, proposing that the first time travel events were not grand gravitational affairs, but the result of the vacuum itself hiccuping through time. At the heart of quantum field theory lies a concept that seems to defy common sense: the idea that a perfect vacuum, what we would think of as completely empty space, is not empty at all. Instead, it is a seething, vibrant sea of activity. Due to the Heisenberg uncertainty principle, energy cannot be precisely pinned down for a short enough time. This allows pairs of virtual particles and antiparticles to spontaneously pop into existence, borrowing energy from the vacuum for a fleeting moment before annihilating each other and paying the energy back. These are called vacuum fluctuations, and they are not just a mathematical curiosity. Their effects have been measured in the lab. This means that at the quantum level, nothing is ever truly still. The void is alive with spontaneous, random creation and destruction. Now, imagine this process occurring in the first instance after the Big Bang, when the entire universe was compressed into a volume smaller than an atom. The energy density was unimaginably high, making the vacuum boil with an intensity we can scarcely conceive. In this ultra-dense environment, the virtual particles flickering in and out of existence weren't just electron-positron pairs. They could have been any particle allowed by the immense energy, and their interactions were far more violent. Under these extreme conditions, a vacuum fluctuation might not have simply created a pair of particles. The tremendous gravitational forces and the warping of space-time could have twisted the very nature of these quantum events. Instead of two particles appearing and disappearing, a fluctuation could have temporarily pinched the fabric of reality so severely that it created a microscopic wormhole, a tunnel through space-time. These wouldn't be the stable, traversable wormholes of science fiction. They would be ephemeral quantum objects lasting for a minuscule fraction of a second. But in the bizarre realm of quantum gravity, where the concepts of before and after are fluid, such a wormhole might not just connect 2 points in space. It could connect 2 points in time. A particle involved in the fluctuation could find itself briefly jumping through this microscopic tunnel and emerging not just elsewhere but elsewhere. It might reappear a planked time into its own past or future before the wormhole pinched off and vanished. These would be the universe's first time travel events, not engineered, not deliberate, but random and probabilistic, driven by the chaotic energy of the newborn cosmos. The significance of these microscopic jumps cannot be overstated. The early universe was a place of incredible uniformity, as evidenced by the cosmic microwave background. Yet somehow, slight overdensities had to form to act as seeds for the galaxies and galaxy clusters we see today. These seeds are thought to be quantum fluctuations stretched to cosmic size by inflation. But what if some of those initial fluctuations weren't entirely random? What if they were influenced by these vacuum time jumps? A particle jumping back and interacting with its own past could have created a tiny, self-reinforcing loop, amplifying a specific fluctuation. This would create a region that was slightly denser than its surroundings, not by pure chance, but because of a causal paradox from the future. In this way, the largest structures in the universe, the vast cosmic web of filaments and voids, might have their deepest roots in the smallest and most bizarre quantum temporal phenomena. The distribution of matter across the heavens could be the frozen fingerprint of countless random time travel events that occurred in the first trillionth of a second of time, a permanent monument to the idea that the universe used time travel as a tool to build itself. But what happens when these potential loops in time create a logical impossibility? This brings us to one of the most famous thought experiments in all of time travel lore, the grandfather paradox. Imagine traveling back in time and preventing your own grandfather from meeting your grandmother. If you succeed, you would never be born, which means you could never have traveled back in time to stop the event in the first place. It's a perfect logical contradiction, a causal loop that seems to shred the very fabric of reality. For decades, this paradox was considered the ultimate proof that time travel was impossible. But what if the universe found a way to solve this problem at the very beginning? What if the first instance of time travel wasn't a paradox at all, but the moment the cosmos established the rules to prevent them from ever happening? This theory proposes that the universe's inaugural journey through time was essentially a stress test for causality, an event that forced the underlying laws of physics to develop a built-in immunity to paradox. In the chaotic moments after the Big Bang, as the first potential closed time-like curves formed, the universe faced a critical juncture. It could either allow paradoxical information to unravel its nascent structure, or it could evolve a set of fundamental rules that would automatically correct or prevent any action that creates an inconsistency. The evidence suggests it chose the latter. The laws we observe today, particularly in the quantum realm, seem perfectly designed to ensure that cause and effect, while they can be bent, can never truly be broken. One compelling way this could work is through the many worlds interpretation of quantum mechanics. In this view, every quantum event causes the universe to branch into multiple, non-communicating realities. Apply this to a potential grandfather paradox. If a time traveler were to attempt to change the past, their action wouldn't alter their own timeline. Instead, the moment they interfere, the universe would split. In one new branch, the grandfather dies and the traveler is never born. But the traveler themselves doesn't vanish. They remain in the original branch from which they came, now merely a visitor in a new, alternate reality they helped create. Their own personal history remains intact and unaltered. The paradox is avoided because the changed past belongs to a new world, not their own. The first time travel event in the early universe could have been the first instance of this branching, a natural mechanism that preserved logical consistency by creating a new timeline whenever a paradox threatened to occur. A different solution comes not from branching worlds, but from the inherent fuzziness of the quantum realm itself, the idea of self-consistent histories. This principle suggests that the only events that are physically possible are those that form a consistent loop from start to finish. The probabilities of quantum mechanics would simply conspire to make any paradoxical action impossible. A time traveler's gun would jam, or they would miss the shot, or a sudden noise would startle them at the crucial moment. The universe would employ a form of preemptive editing, ensuring that any action taken in the past was always a part of history. In this scenario, the first time travel event wasn't a dramatic alteration of history, but a quiet, seamless integration of information into the timeline. A particle traveling back would have always been there, its presence in the past a fundamental and unchanging part of the causal chain that led to its own journey. The universe's first act was to prove that you can't change the past because the past already includes your attempt to change it. The beauty of these theories is that they transform the grandfather paradox from a fatal flaw into a powerful clue. The very fact that we can conceive of such a paradox, yet our universe continues to operate with perfect logical consistency, suggests that the laws of physics have already solved the problem. The first time travel event was the cosmos learning to tie its own shoes, establishing a set of rules where time could be flexible and interactive without ever becoming self-contradictory. This inherent robustness might be the greatest legacy of the universe's first temporal experiment, a fundamental guarantee that reality will always make sense, no matter how deeply we twist it. While the quantum foam of the early universe was a chaotic sea of fleeting temporal jumps, another, more stable structure might have been forming, one that could turn these random flickers into the first reliable rhythms of time travel. This brings us to an astonishingly exotic state of matter that blurs the line between time and substance, the time crystal. Unlike any other form of matter, a time crystal structure doesn't just repeat in space like the atomic lattice of a diamond. It repeats in time, oscillating in a perpetual cycle of motion even in its ground state, its state of lowest energy. It consumes no energy to maintain this eternal rhythm. It is a clock that winds itself, a fundamental beat in the fabric of reality that never, ever winds down. The formation of such an object in the primordial universe is a staggering concept. In the incredible density and pressure of the first moments after the Big Bang, the conditions would have been unlike any we can recreate. As the superforce of nature began to split into the four fundamental forces we know today, this phase transition could have created topological defects, not just the cosmic strings we discussed earlier, but even more bizarre structures. Fluctuations in the earliest quantum fields might have locked into a configuration where the lowest energy state wasn't a state of rest, but one of perpetual, periodic motion. Think of it like a cosmic gel that, once set, continues to jiggle forever without any additional push. These first time crystals wouldn't have been large, they could have been microscopic, even subatomic in scale. But their impact would have been profound, for they would have created the first stable, self-sustaining loops in time. This is where the concept transforms from a curiosity into a potential mechanism for the universe's first time travel. A time crystal's constant oscillation establishes a fixed, periodic rhythm in time. In the frenzied environment of the early cosmos, such a stable rhythm could have acted as an anchor. If a particle or a packet of quantum information became entangled with a time crystal's oscillation, its own timeline could have become locked into that perpetual cycle. It wouldn't be traveling forward in a linear fashion. It would be cycling through a fixed segment of time, repeating the same interval over and over again. For that particle, a picosecond of the universe's history would be an eternal present, a closed loop from which it could not escape. The time crystal would be less a vehicle and more a prison of time, a trap that caught the first temporal travelers in an endless dance. But what if these ancient time crystals didn't just trap particles? What if they facilitated a transfer of information? The oscillation of a time crystal creates a regular, predictable distortion in the local spacetime around it. This distortion could theoretically open a minuscule, stable wormhole, a tunnel not just through space but through time, that pulses open and closed in perfect sync with the crystal's rhythm. Information could pass through this tunnel during the open phase of the cycle, jumping from one point in the timeline to another before the passage pinched shut again. This would be a far more reliable form of time travel than the random quantum fluctuations we discussed earlier. It would be a scheduled service, a temporal railway running on a fixed timetable set in the first moments of creation, allowing data to be shuttled between different eras of the infant universe. The most incredible possibility is that these primordial time crystals might still be with us today. Because they exist in their ground state and don't expend energy, there's no thermodynamic reason for them to decay. They could be floating through the universe right now, invisible relics from the dawn of time. Their perpetual motion would be undetectable to most instruments, as they don't radiate energy or interact with light in a normal way. However, we might find them by their gravitational signature. Their unique, oscillating structure would create an equally unique, oscillating gravitational field, a rhythmic, predictable tug on spacetime that advanced instruments like future generations of gravitational wave observatories might one day detect. Finding one would be like discovering a fossilized clock from the Big Bang itself, still ticking after 14 billion years. If they do exist, they would be the ultimate evidence of a universe built with time travel as a foundational feature. They wouldn't be a human invention to be achieved in some distant future, but a natural part of the cosmos's original operating system. Their discovery would revolutionize our understanding of time, proving it is not a passive stage on which events play out, but an active, dynamic dimension that can be structured and harnessed, just like the three dimensions of space. The time crystal wouldn't just be a theory, it would be a physical artifact, a piece of the universe's first machinery for navigating time, waiting for us to finally understand what we are looking at. We've explored how the universe might have bootstrapped its own arrow of time during the Planck epoch, but how did that initial directional bias become the rigid, one-way street we experience today? To understand that, we must venture into a process that acts as the gatekeeper between the weird quantum world and our familiar classical reality, quantum decoherence. This theory proposes that decoherence didn't just help define our reality, it may have been the very mechanism that permanently locked in the arrow of time, creating the first firm boundary between the past and the future. At its heart, quantum decoherence is about the loss of quantum magic. In isolated quantum systems, particles can exist in a superposition of multiple states, like Schrödinger's famous cat being both alive and dead. They can also be entangled, sharing a spooky connection that defies distance. However, this delicate state is incredibly fragile. The moment a quantum system interacts with its external environment, even just a single photon of light bouncing off it, it becomes irrevocably entangled with that environment. This process forces the superposition to collapse into a single, definite state. The quantum probabilities resolve into a concrete outcome, and the weirdness vanishes, replaced by the predictable behavior we see in our everyday world. Decoherence is the reason we don't see tables and chairs in superpositions. They are constantly interacting with air molecules and light, which continuously measure them and force them into a classical state. Now apply this concept to the entire universe in its first moments. Initially, the cosmos was an incredibly small, hot, and dense system. In such a state, everything was interacting with everything else. There was no external environment. The entire universe was one single, massively entangled quantum system. In this primordial soup, the distinction between past and future was likely still fuzzy, a relic of the time-symmetric microscopic laws. But as the universe expanded and cooled at a ferocious rate, it created something that had never existed before: space. And with more space came the possibility of isolation. Different regions of the universe could slowly stop interacting with each other as the space between them expanded faster than light could travel. This was the moment of the first great environmental separation. This is where decoherence permanently etched the arrow of time into the cosmos. As regions of space became causally disconnected, they effectively became each other's environment. The quantum information that was once shared across the entire unified system became lost, irretrievably scrambled across the vast and growing distances. This process of decoherence happening on a cosmic scale wasn't symmetrical. It only moved in one direction, from a state of perfect quantum coherence to a state of increasing classical definiteness and separation. This irreversible loss of quantum information is deeply connected to the concept of entropy, the measure of disorder that defines our arrow of time. Decoherence provided the mechanism that made the universe's increasing entropy not just a statistical likelihood, but a fundamental one-way process. It built the first temporal wall, making the past a fixed and unchangeable record of collapsed quantum states, while the future remained a realm of open probability. This leads to a breathtaking and theoretically profound idea for time travel. If decoherence is what solidified the past, then reversing decoherence could, in principle, make the past fuzzy again. It would be like unscrambling an egg, a monumental task that seems to defy thermodynamics. But on a quantum level, if we could somehow gather all the environmental information that a system has become entangled with and reverse its interactions, we could, in theory, undo the collapse. We could force a decohered, classical system back into its original superposition, effectively erasing the fact that a measurement ever happened. This would not be time travel in the sense of a physical journey, but an informational one. By reversing decoherence, you could return a quantum system to its state at a previous point in time, effectively sending its quantum information backwards along its own timeline. Scaling this idea up to the universe's first moments is the stuff of ultimate speculation, but it points towards an incredible possibility. The cosmic microwave background radiation is the oldest light in the universe, the afterglow of the Big Bang. It is also the result of a massive decoherence event, the moment when photons decoupled from matter and finally stopped interacting, allowing them to travel freely across the cosmos. That light carries with it the imprint of the environmental interactions that collapsed the universe's earliest quantum states. In a sense, it is the permanent record of that first great decoherence. The theoretical time travel proposition is this: if a future civilization with godlike technology could somehow capture and analyze every single photon of the cosmic microwave background, along with every other particle that has been scattered across the universe, they might be able to perform the ultimate calculation. They could reverse engineer the decoherence process for the entire visible cosmos, winding the quantum tape backwards to peer into the superpositions that existed before the first temporal boundaries were set. They wouldn't be traveling to the past, they would be computationally reconstructing it, undoing 14 billion years of environmental entanglement to witness the universe in its first pristine quantum state. This holographic view of reality completely redefines what time travel could be. Instead of a physical journey through a temporal dimension, it becomes an act of information retrieval and rewriting. If our three-dimensional reality, including time, is a projection from a two-dimensional surface, then the entire history of the universe, every event from the Big Bang to this very moment, is encoded on that cosmic boundary, much like the data on a Blu-ray disc encodes a seemingly three-dimensional movie. To travel to a different time wouldn't require a machine that moves through time, but a technology that can read from and, crucially, write to a different sector of that underlying data surface. You wouldn't be moving your body to the past, you would be editing the projection parameters so that your local region of space-time reflects the information that describes a different era. The mechanism for this is as elegant as it is bizarre. The holographic principle suggests that the information for every particle's position, state, and moment in time is stored on the distant boundary. To access a past event, you wouldn't need to fight the universe's entropy or generate impossible energies. You would simply need to locate the specific data bits that correspond to that event and make them the active source for your local projection. It would be like a film editor finding a specific frame in a movie and splicing it into the live broadcast. Your consciousness and your immediate surroundings would then experience that moment as the present, effectively immersing you in a perfectly reconstructed past. The past in this model isn't gone, it's merely data stored in a different location on the universal hard drive, waiting to be accessed. This perspective offers a stunning solution to the most intractable time travel paradoxes. In a holographic universe, you cannot create a true grandfather paradox because you are not actually changing the past. The original primary data on the boundary remains untouched and immutable, encoding one single, consistent history of the universe. Any time travel would be a local manipulation of the projection, creating a temporary bubble of altered space-time that is consistent within itself but does not rewrite the foundational code. If you were to go back and interact with events, you would not be altering your own original timeline. You would be creating a new, self-consistent branch of the projection, a parallel experience spun off from the main data stream, where your actions are part of a new, internally logical sequence. The universe's underlying data remains paradox-free, preserving the consistency of the one true historical record while allowing for local excursions into what might have been. The most profound implication is that the very first instance of time travel might have been built into the universe at its birth. The holographic principle is deeply connected to black hole thermodynamics and the nature of information. At the instant of the Big Bang, the universe was an incredibly hot, dense, and seemingly featureless point. According to this theory, the information needed to project our entire cosmic history was imprinted onto its boundary at that very moment. The initial conditions set not just the laws of physics, but the entire four-dimensional movie that was to follow. However, if the boundary conditions were not perfectly static, if there was any fluctuation or interaction in that lower dimensional realm, it could have caused ripples in the projection, creating temporary and localized anomalies where the flow of time stuttered, skipped, or even briefly reversed. The first time travel may not have been a dramatic event in our dimension, but a subtle glitch in the source code of reality, a fleeting moment when the cosmic projector flickered and showed a frame out of order, establishing the potential for time travel as a fundamental, though hidden, feature of a holographic cosmos. Yet for all the grandeur of holographic projections and cosmic boundaries, some of the most compelling evidence for the universe's first time travel might be found in the quietest, most ghostly particles ever detected. To understand this, we must shift our perspective from the vast architecture of space-time down to the behavior of a single, nearly imperceptible subatomic particle, the neutrino. Billions of these elusive entities are passing through your body every second, leaving almost no trace of their presence. They are the universe's ultimate ghosts, and their strange behavior might hold the key to a form of time travel so subtle it has been happening undetected since the first moments of the Big Bang. Neutrinos are born from some of the most violent and energetic processes in the cosmos. The nuclear fusion at the heart of stars, the cataclysmic explosions of supernova, and of course, the unimaginable furnace of the universe's birth. What makes them so bizarre is their ethereal nature. They have a vanishingly small amount of mass, no electric charge, and they only interact with other matter through the weak nuclear force and gravity. This means they can fly through entire planets as if they weren't even there, but their most peculiar feature is a quantum quirk known as oscillation. As a neutrino travels through space, it doesn't maintain a single, fixed identity. Instead, it spontaneously morphs between three different flavors: electron, muon, and tau neutrino. This isn't just a change in property, it's a fundamental transformation of the particle's quantum state. This process of oscillation is where the concept of time travel enters the picture. In the quantum world, a particle's flavor state and its mass state are not the same thing. A neutrino that is produced as a specific flavor, say an electron neutrino, is actually a quantum mixture of three different mass states. As it moves, these mass states evolve at slightly different rates due to their tiny mass differences. It is the interference between these evolving mass states that causes the neutrino to appear to change flavor. Now, here is the crucial part. The rate at which this oscillation happens depends on the neutrino's energy and the distance it travels. For a neutrino, the act of traveling through space is intrinsically linked to a cyclical evolution through different quantum identities. Its journey is not just through space, but through a periodic loop of its own possible states. Now, cast this phenomenon back to the very first second of the universe. The density and energy were so extreme that neutrinos, which today barely interact with anything, were trapped in a hot, dense soup of particles, constantly colliding and interacting. But as the universe expanded and cooled to around 1 second old, it underwent a pivotal change known as neutrino decoupling. Suddenly, the cosmos became transparent to these particles. They were set free, streaming out in all directions, and they have been traveling almost entirely uninterrupted for the last 13.8 billion years. The very first neutrinos are still out there, carrying with them a pristine record of the universe's infancy. This is where their oscillation becomes a form of time travel. The quantum state of a neutrino is not just defined by its present moment. Its oscillation is a process that ties its past to its future. The specific way it oscillates depends on the exact conditions of its birth. The energy, the density, the very flavor it was born as in the early universe. In a very real sense, the oscillation pattern of a relic neutrino from the Big Bang is a living fossil, a quantum memory of its own origin. By measuring its state today, we are not just seeing a particle as it is now, we are indirectly sampling information from the moment it was created. The neutrino's continuous oscillation is a bridge across time, connecting its present reality directly back to its first moment of existence. It is a particle that is forever linked to its own past through its immutable quantum rhythm. The most profound implication is that these ancient neutrinos might not just be remembering the past, they could be effectively reliving it. If the conditions in the modern universe were to somehow perfectly mirror the conditions of the early cosmos, a concept that exists in certain cyclic or bouncing universe models, a neutrino's oscillation could become synchronous with its original state. It could, in a quantum sense, return to the exact same flavor mixture it had at the moment of decoupling. For that particle, the billions of years in between would vanish from its experiential timeline. It wouldn't have experienced a linear flow of time, but a closed loop, returning to its original quantum state as if no time had passed at all. This wouldn't be time travel in the science fiction sense of a journey, but a temporal resonance, a vibration in the particle's identity that harmonizes across the eons, making the first second and the present moment one and the same for the neutrino. But to find evidence of these first temporal events, we don't necessarily need to look for faint gravitational waves or hunt for ancient particles. The answers might be hiding in the oldest photograph ever taken, a picture of the infant universe that surrounds us every single day. This is the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills every cubic inch of the cosmos. For decades, cosmologists have studied the tiny temperature variations in this radiation, the hot and cold spots that are the blueprints for all future galaxies and galaxy clusters. These fluctuations are typically explained by density waves in the early universe, amplified by inflation. But a radical hypothesis suggests that this ancient light might contain a far more exotic signature, the faint but detectable echoes of the universe's first time travel events. The concept rests on a simple but profound principle. Any event that significantly warps the fabric of space-time leaves an indelible mark on the light passing through it. A gravitational wave from a black hole merger, for instance, stretches and compresses space as it travels, leaving a distinct pattern on the cosmic microwave background polarization. In the same way, a macroscopic time travel event such as the formation of a stable wormhole, the movement of cosmic strings, or a large-scale quantum time jump would have created a massive disturbance in the gravitational field of the early universe. This disturbance would have rippled outward, imprinting a unique and anomalous pattern on the photons of the cosmic microwave background as they began their journey across the cosmos nearly 14 billion years ago. These wouldn't be the random hills and valleys of standard density fluctuations, but something more structured like a concentric circular pattern, a bizarrely straight edge, or a region where the temperature statistics defy all standard inflationary predictions. The most promising place to look for these temporal signatures is in the polarization of the cosmic microwave background, specifically in what is known as the B-mode polarization pattern. While inflation is expected to create a specific type of B-mode pattern from primordial gravitational waves, a time travel event would create a different kind of distortion. For example, if a wormhole briefly stabilized and allowed information to flow between two different eras, the gravitational tug of war around its mouth could have twisted the polarization of the light in a unique, swirling pattern. If two cosmic strings moved past each other and created a closed time-like curve, the event might have left a telltale linear discontinuity in the temperature map, a straight-line scar etched onto the sky that cannot be explained by any known physical process. Finding such an anomaly would be like discovering a fossilized footprint of a time traveler in the first solid ground of the cosmos. The search for these echoes is already underway, driven by a new generation of incredibly sensitive telescopes located at the South Pole and high in the Chilean Andes. These instruments are not just mapping the temperature of the cosmic microwave background with unprecedented precision. They are meticulously charting its polarization, looking for any pattern that seems out of place. The challenge is immense as the signal from inflation is incredibly faint, and any time travel signature would be even fainter, buried under layers of noise from our own galaxy and the instruments themselves. It is a painstaking process of statistical analysis, searching for a needle in a cosmic haystack. But if such a signature were ever confirmed, it would revolutionize our understanding of reality, providing the first tangible evidence that the universe's timeline is not a simple straight line, but a complex tapestry woven with threads that loop back and connect to themselves. It would mean that the potential for time travel is not a futuristic fantasy, but a fundamental part of our cosmic heritage, with its proof written in the ancient light that has been bathing the universe since the very beginning. To truly grasp the edge of time, we must venture beyond Einstein's relativity and into the uncharted territory where gravity itself becomes a quantum creature. This is the realm of quantum gravity, a field of physics that seeks to describe the force that shapes the cosmos using the bizarre rules that govern the subatomic world. One of its most profound suggestions is that time, as we experience it, may not be a fundamental ingredient of the universe. Instead, it could be an emergent property, a collective illusion that arises from the interactions of countless tiny quantum events, much like the concept of temperature emerges from the jostling of molecules. This leads to a staggering possibility. If time emerged, then there was a state of reality that existed before time itself began, a pre-temporal phase of the cosmos that we might one day learn to access. What could before the Big Bang possibly mean if time didn't exist? It's a question that seems to tie our brains in knots because our very language and logic are built upon a framework of cause preceding effect. In a timeless state, there is no before and no after. There is only existence, perhaps as a static, frozen geometry of relationships, a vast network of quantum connections without any flow or sequence. Think of it like the individual frames of a movie film scattered on the floor. Each frame exists containing a full snapshot of reality, but there is no order to them until they are threaded through a projector, which creates the illusion of motion and a flowing timeline. In this view, the Big Bang wasn't the first event in a sequence. It was the moment the cosmic projector first clicked on, taking that timeless quantum state and unfurling it into the four-dimensional spacetime we inhabit. This perspective completely transforms the concept of time travel. A conventional time machine would move you along the already created film strip of history, from one frame to an earlier or later one. But a technology based on quantum gravity would be something far more radical. It wouldn't move you through time. It would allow you to step outside of time entirely, into the projector room where all the frames exist at once. From that vantage point, you wouldn't be traveling to the past or future. You would be accessing a deeper layer of reality where all moments are equally real and present. You could, in theory, observe any frame you wished or even potentially alter the order in which they are projected, effectively rewriting the timeline from its source code. The mechanism for such an incredible feat would lie in manipulating the very quantum processes that give rise to time. In some loop quantum gravity models, spacetime is not smooth and continuous but is composed of tiny, discrete grains or loops, a kind of quantum foam at the Planck scale. The flow of time emerges from the way these grains interact and entangle with one another. If we could find a way to control these interactions on a massive scale, we could, in principle, locally reverse the process that creates time's arrow. We could cause the quantum grains in a specific region to decohere in the opposite order, making entropy decrease and time appear to run backwards within that bubble. Or we could temporarily freeze their interactions altogether, creating a zone of truly timeless stasis. This wouldn't be navigation, it would be fundamental reality editing, reaching into the source of temporal emergence and twisting the dials. The ultimate goal of such technology would be to access the pre-Big Bang state, that timeless architecture from which our universe was projected. What would we find there? It might be a landscape of breathtaking mathematical beauty, a set of initial conditions and laws waiting to be activated. Or, according to theories like the no-boundary proposal, it could be a smooth, self-contained geometry with no singularities and no beginning, where the very idea of a start is replaced by a gentle quantum rounding off. Journeying to this state would be the final and greatest act of time travel, not because it would take us to a moment in our past, but because it would take us to the foundation of reality itself, the silent, eternal realm that exists beneath the comforting but illusionary flow of time. But what if the key to understanding the universe's first time travel isn't found in the bright, visible matter that forms stars and planets, but in the mysterious, invisible substance that holds it all together? We now turn our attention to the shadowy bulk of the cosmos, the enigmatic force known as dark matter. This invisible material makes up roughly 85% of all matter in the universe, yet it refuses to interact with light, revealing itself only through its gravitational pull on galaxies. But could its influence extend beyond shaping the cosmos in space? This theory proposes that dark matter's most profound effect might be on time itself, and that in the dense early universe it could have created the first and most powerful natural time machines. To grasp this, we need to revisit Einstein's principle that gravity is the curvature of space-time. The more mass you have in one place, the more it warps the fabric of reality, slowing down time in its vicinity. We see this with ultra-precise clocks on GPS satellites, which run slightly faster in Earth's weaker gravity than identical clocks on the surface. Dark matter, by its sheer abundance, is the dominant gravitational force in the universe. It forms vast, diffuse halos around every galaxy and creates an invisible scaffolding upon which the visible cosmos is built. Where dark matter is most concentrated, its gravitational pull is strongest, and therefore, time should pass more slowly relative to areas with less dark matter. This means that two clocks placed in different parts of the universe, one in a dense dark matter cloud and one in a void, would tick at different rates. The universe, in essence, has never had a single universal clock. It has always been a patchwork of different temporal flows, dictated by the hidden distribution of dark matter. Now cast this idea back to the universe's first few 100 million years. This was the era of the first galaxies, a time when the cosmos was much smaller and far denser than it is today. Dark matter, fresh from the Big Bang, was also far more concentrated, clumping together under its own gravity into dense knots and filaments long before normal matter could collapse to form the first stars. In these primordial hubs of dark matter, the gravitational time dilation would have been extreme. A region with a sufficiently high density of dark matter could have functioned as a natural time capsule, a bubble where the flow of time was slowed to a near standstill relative to the rapidly evolving universe outside. For a particle or a packet of information caught in such a bubble, billions of years could have passed in the wider cosmos while it experienced only a few fleeting moments. If it was somehow released, it would effectively make a gigantic leap into the future. The implications for the first time travel are profound. These dark matter time dilation fields wouldn't require any advanced technology or exotic physics. They would be a simple gravitational consequence of the universe's own structure. The first time travelers could have been ordinary particles of normal matter, protons, electrons, or even complex molecules that simply wandered into one of these temporal traps. They would have been preserved in a state of suspended animation for eons before eventually drifting out or being disturbed by a galactic collision, re-entering a universe that had aged dramatically without them. This process could explain some of the mysterious, ancient structures we see in the cosmos, like stars that appear older than the universe itself. Perhaps they formed in these slowed time zones where their internal clocks ticked far more slowly, allowing them to achieve great age by their own measure while the universe was still young. The true temporal power of dark matter might be even stranger than simple slowing. Some theoretical models suggest that dark matter could be composed of particles that don't just create gravity, but that interact with the fabric of time in a unique way. Certain candidates for dark matter, like actions or sterile neutrinos, are theorized to have peculiar quantum properties that could make them susceptible to fields beyond standard gravity. If these particles interact with a hypothetical temporal field, or if their presence somehow stabilizes microscopic wormholes, then concentrations of dark matter could do more than just slow time. They might twist it into closed loops or create brief bridges to other eras. The greatest time machines in the universe may not be of our making. They could be the silent, invisible halos of dark matter that have surrounded every galaxy since the dawn of time, their immense gravitational presence forever bending the river of time to their will, hiding the secret of temporal travel in the darkest corners of the cosmos. This concept of a holographic universe leads us directly to one of the most profound ideas about time's origin, that the very first transfer through time wasn't a transfer of matter or energy, but of pure information. At its heart, this theory suggests that information is the most fundamental currency of reality, more basic than particles or forces, and that the universe's inaugural temporal journey was a quantum information event, a single bit of data finding a way to loop back on its own timeline. To understand how this could work, we must confront one of the most famous puzzles in modern physics, the black hole information paradox. The paradox begins simply enough. According to Einstein's general relativity, when something falls into a black hole, it is lost forever, crushed into the singularity. Its mass, charge, and angular momentum are added to the black hole, but every other detail about it, what kind of particle it was, its quantum state, its spin, seems to vanish from our universe. This presents a catastrophic problem for quantum mechanics, which holds that information can never be truly destroyed. It can be scrambled, hidden, or made incredibly difficult to read, but it must always, in principle, be preserved. So, when a black hole eventually evaporates away through Hawking radiation, what happens to all that information it swallowed? If it's truly gone, quantum mechanics is wrong. If it's not, it violates relativity. This is the information paradox, a clash between our two most successful theories of reality. One compelling solution, championed by physicists like Leonard Susskind, involves the holographic principle we just explored. It proposes that the information about everything that falls into a black hole isn't destroyed at all. Instead, it is perfectly encoded onto the black hole's event horizon, its two-dimensional boundary. Every particle, every atom, every book that ever fell in leaves a tiny, scrambled imprint on this spherical surface. When the black hole radiates, it doesn't release random noise. It releases Hawking radiation that is subtly imbued with this encoded information, slowly and faithfully leaking the data back out into the universe over eons. The information was never lost. It was just translated onto a lower dimensional surface and transmitted back out over an immense timescale. Now, take this concept and apply it to the entire cosmos. The universe itself, in its first moments, was an incredibly hot, dense state, not unlike the interior of a black hole. The holographic principle suggests that the information describing our entire three-dimensional universe, including the dimension of time, is encoded on its two-dimensional boundary at infinity. This means that every event, every particle interaction from the Big Bang to this very second, is permanently etched onto this cosmic data storage system. The flow of time, in this view, is the process of this information being read out and projected into the volume of the universe. The past isn't gone, it's simply data that has already been processed. The future is data waiting to be read. This is where the mechanism for the first quantum information time transfer emerges. In the seething quantum foam of the Planck epoch, the distinction between the interior of the universe and its boundary was likely meaningless. A quantum fluctuation, a random bit of information, could have briefly created a connection, a kind of microscopic wormhole between the present moment in the volume and its corresponding point on the boundary. Through this connection, that bit of information could have been written to the boundary, but because the boundary encodes the entire timeline, writing to it is not writing to a spatial location, it's writing to a temporal one. That information could then be accessed by a different point in the timeline, effectively allowing data to be sent from the present to the past or future. Imagine a single quantum bit, a qubit, fluctuating into existence in the first nanosecond of the universe. Through this process, its information is instantaneously transcribed onto the cosmic boundary. A moment later, another fluctuation at a different point in the early cosmos reads that exact same data from the boundary. From the perspective of the timeline within the universe, that information has just traveled backward in time. The first bit was the effect, the second bit reading it was the cause. This creates a self-consistent, closed loop in time, where information ensures its own existence without a traditional origin point. The universe didn't need a machine to achieve this. It used its own holographic architecture to perform the first act of time travel, establishing a feedback loop where the future could subtly influence the past to bring about its own stable existence, potentially explaining the mysterious fine-tuning we observe today. But what if the particles that make up our very being have hidden partners, mirror images that live their lives in reverse? This leads us to a theory that connects the hunt for new physics directly to the nature of time itself, supersymmetry. This elegant concept is a proposed extension of the standard model of particle physics, designed to solve some of its most nagging problems, like the mystery of dark matter and the weakness of gravity. At its heart, supersymmetry, or SUSY for short, proposes that every known particle has a hidden superpartner. For every electron, there's a hypothetical selectron. For every quark, a squark. These particles would have different quantum properties, most notably their spin, and would have been abundant in the high-energy furnace of the early universe. The connection to time travel lies in how these particles might interact with the dimension of time. Some formulations of supersymmetry suggest that the transformation between a particle and its superpartner could be intimately linked to a reversal of time's arrow. Think of it as a fundamental mirror. In our everyday experience, a particle and its particle partner would be distinct entities, but under the extreme conditions of the early cosmos, that mirror might have been blurred. A particle vibrating at a specific, immense energy could have momentarily flickered into its supersymmetric partner, and in that instantaneous transformation, its personal experience of time might have briefly inverted. It wouldn't be traveling along a timeline, it would be flipping its own internal clock. Imagine the universe in its first moments, a dense plasma where particles and energy were colliding at frequencies we can scarcely imagine. In this chaos, supersymmetric transformations could have been happening constantly. An electron, for a fleeting fraction of a second, becomes a selectron. From our perspective, that selectron is a new particle, but from the perspective of the particle's own timeline, that transformation might represent a jump. If the selectron state experiences time as reversed relative to the electron, then the moment it emerges could be causally connected to a point in its own past. It's a difficult concept to visualize, but imagine a single vibration in a string where the upward motion is the particle moving forward in time, and the downward motion is the particle moving backward. The entire early universe could have been a symphony of these temporal oscillations. This wouldn't be time travel in the macroscopic sense of sending a complex object back to change history. Instead, it would be a fundamental subatomic process where the very concepts of before and after were constantly being renegotiated at the most basic level of reality. These countless microscopic time reversals could have had a profound effect on the evolution of the cosmos. They might have provided a mechanism to smooth out the universe, explaining its incredible large-scale uniformity. Or they could have been the random number generator that set the values of the fundamental constants, with each fleeting temporal flip influencing the probabilities of quantum outcomes. The fine-tuning of the universe for life might not be a bizarre coincidence, but the natural result of a vast number of supersymmetric time mirrors acting as a cosmic feedback loop, ensuring stability through countless tiny corrections across time. While evidence for supersymmetry has remained elusive in our current particle accelerators, its potential role in the universe's first second offers a breathtaking glimpse into a deeper, more symmetrical layer of reality where time itself is a two-way street. To truly push the boundaries of cosmic origins, we must venture beyond the confines of our own universe and into the vast, hidden dimensions predicted by string theory. This framework suggests that the fundamental particles we see are not tiny points, but incredibly small, vibrating loops of energy. For these vibrations to make mathematical sense, they require more than the 3 dimensions of space and 1 of time we experience. They need a reality composed of 10 or even 11 dimensions. Most of these extra dimensions are imagined to be curled up and compactified, too small for us to perceive. But one radical idea proposes that our entire cosmos is actually a 3-dimensional island or a membrane floating within this higher dimensional space. This is the brain world scenario, and it sets the stage for one of the most dramatic theories of creation and time travel ever conceived. Imagine 2 such membranes, 2 parallel universes, drifting silently through a higher dimensional bulk. They are separated by a minuscule distance in an extra dimension we cannot see. According to this model, these branes are not static. They can move, oscillate, and even collide. The theory proposes that our Big Bang was not a singularity from nothing, but the cataclysmic result of such a collision. When our brain smashed into another, the immense energy of that impact was converted into the hot, dense plasma that became our expanding universe. It was the ultimate cosmic car crash, and the moment of impact was the first tick of our cosmic clock. But the aftermath of such a violent event would not have been limited to creating matter and energy. It would have sent powerful shockwaves rippling through the very fabric of space-time. These wouldn't be ordinary gravitational waves. The collision would have created profound distortions in the geometry of our brain, generating massive ripples that propagated not just through space but through time as well. Think of it like dropping a boulder into the pond of time itself. The initial splash is the Big Bang, but the concentric waves that radiate outward are ripples in the temporal dimension. These temporal ripples would represent zones of highly warped chronology, regions where the normal, linear flow of cause and effect is twisted and folded. A sufficiently powerful ripple could theoretically curl back on itself, creating a closed time-like curve, a natural pathway that connects one era of the universe to another. The mechanism for time travel here is built directly into the architecture of reality. A spacecraft wouldn't need a fancy machine. It would simply need to navigate to the precise location where one of these ancient temporal ripples is cresting or troughing. By entering this region of extreme temporal curvature, the ship and its crew could find themselves transported along the ripple, surfing the wave to a different point in cosmic history. They might ride the crest of the wave forward to the universe's distant heat death, or dive into the trough to be carried backward to the era of the first stars. The brain collision didn't just create our universe, it imprinted it with a hidden network of temporal currents, a permanent record of its own violent birth that could be used to navigate the ocean of time. The most fascinating evidence for this incredible idea might be written in the sky. The cosmic microwave background is a snapshot of the universe just 380,000 years after the Big Bang. If our cosmos was born from a brain collision, the immense energy of that impact should have left an indelible imprint on this ancient light. Specifically, physicists calculate that such an event would have generated a very specific pattern of gravitational waves, which in turn would have polarized the cosmic microwave background in a unique way, creating a distinct swirling pattern known as B-mode polarization. While experiments are still searching for this definitive signal, its discovery would be powerful, albeit indirect, evidence that our universe began with a collision that could have woven the potential for time travel directly into the foundation of everything we know. Imagine a process so precise it can dismantle the exact quantum state of a particle in one location and perfectly reassemble it somewhere else without the original particle ever physically crossing the distance between them. This isn't science fiction, it's quantum teleportation, a real protocol that relies on the spooky connection of entangled particles to achieve what looks like magic. Now, stretch this concept across the entire cosmos and consider its implications not just for moving through space, but for navigating time itself. At the heart of this protocol is a mechanism called entanglement swapping, a way to entangle two particles that have never directly interacted by using a third mediating particle. This creates a chain of correlation that can, in theory, link events across vast stretches of spacetime. If we apply this on a cosmic scale, entanglement swapping could create a web of connection that binds different moments in the universe's history, making the transfer of quantum information from the past to the future not just possible, but a fundamental feature of reality. To grasp how this becomes a form of time travel, think of the universe not as a collection of objects, but as a network of quantum relationships. In the fiery first moments after the Big Bang, particles were born in a state of profound entanglement, their fates intertwined. As the universe expanded, these particles were carried apart by the stretching of space itself, but their quantum connection remained, a ghostly thread linking them across billions of light years. Entanglement swapping provides a way to activate these ancient links. A sophisticated observer in the present could perform a specific measurement on a locally entangled pair of particles, a measurement that doesn't just affect them, but instantly projects its influence down the chain to their long-lost partner from the dawn of time. This action would effectively force the ancient particle into a specific quantum state, a state chosen by the measurement happening now. From a certain perspective, information has just been sent backward through time, not by moving faster than light, but by leveraging a pre-existing connection that transcends both space and time. This creates a scenario where cause and effect are no longer bound by a simple linear sequence. The measurement in the present becomes the cause for the state of the particle in the past. It's a closed loop in time, a quantum feedback mechanism where the future directly influences the past to ensure its own consistent existence. The universe's first act of time travel, then, might not have been a dramatic journey, but the quiet, constant hum of this quantum dialogue. As the early universe cooled and its structure formed, these teleportation links could have acted as a cosmic calibration system. Fluctuations in the density of matter, the seeds of future galaxies, might have been subtly shaped by information feedback from their own successful future states, a self-reinforcing loop that ensured the cosmos would evolve in a stable and life-permitting way. The fine-tuning we observe might be the result of the universe whispering instructions to its younger self through the quantum teleportation channels woven into its very fabric. But if our universe is just one bubble in a vast cosmic foam, how did it become so stable and isolated? This brings us to a theory that stretches the concept of the multiverse to its absolute limit, proposing that the boundaries between these infinite worlds might not be impenetrable walls, but dynamic membranes that could allow for the most incredible form of time travel. This is the concept of eternal inflation, a model where the vacuum energy that drove our universe's rapid expansion is not a one-time event, but a perpetual, unstoppable force. In this eternal sea of high-energy, false vacuum, random quantum fluctuations continuously trigger the formation of new, bubble universes, each with its own unique laws of physics and its own beginning. Our cosmos is just one bubble among an infinite number, constantly drifting further apart in an ever-expanding multiversal ocean. The boundaries where these bubble universes collide or gently press against each other are regions of unimaginable energy and density. When two such bubbles meet, their walls or brains interact, creating a shockwave of cosmic proportions. It is within these violent, hyper-dimensional intersections that a remarkable possibility emerges. The incredible forces at play could warp the fabric of spacetime so severely that they stitch the timelines of the two universes together, creating a natural wormhole, a tunnel through the higher dimensional bulk that connects not just two points in space, but two entirely different cosmic epochs. Because each bubble universe is born at a different time in the eternal inflationary background, their internal clocks are not synchronized. A tunnel connecting our universe to a neighboring one could easily link our present to their distant past or our infancy to their heat death. Imagine a civilization advanced enough to locate and navigate to such a boundary region. They wouldn't need to build a complex time machine. They would simply need to find the cosmic shore where their universe meets another and venture into the temporal rift. By passing through this natural bridge, they might emerge into a universe that is billions of years younger or older than their own. For them, it would be a journey into the deep past or the far future, but it would be the present for the inhabitants of that other world. This form of time travel is less about moving along your own timeline and more about switching to a parallel timeline that is at a different point in its evolution. The eternal inflationary medium acts as a higher dimensional landscape where all of time, past, present, and future for every possible universe exists simultaneously, and these bubble collisions create the temporary roads that connect them. The implications for our own origin are profound. If such temporal bridges exist, our universe may not have started from a pure, isolated nothingness. The Big Bang could have been seeded or influenced by information that traveled through a wormhole from a pre-existing, older universe in the inflationary sea. This would mean that the laws of physics we observe, which seem so perfectly tuned for life, might not be a random accident of our particular bubble, but an inheritance. They could be the result of a selection process that has been ongoing across countless universes for eternity, with stable, life-permitting configurations being passed through temporal bridges to newborn cosmoses. In this view, the first time travel event might not have occurred within our universe at all, but could have been the transfer of the very quantum blueprint that made our existence possible from a long-dead parent universe to our own at the moment of its creation. But what if the key to the universe's first journey through time has been with us all along, not in the fabric of space-time or the laws of physics, but in the very nature of our own minds? This theory ventures into the most profound and controversial intersection of cosmology, quantum mechanics, and philosophy, proposing that consciousness is not a passive byproduct of the universe, but an active participant in shaping reality, and that its emergence may have been the ultimate temporal event. This is the consciousness-time interface, the idea that the act of observation doesn't just measure the world, but in a very real sense creates it, reaching across time to finalize a past that was until then only a haze of potential. To understand this, we must return to one of the most baffling puzzles in all of science, the quantum measurement problem. In the subatomic world, particles exist in a state of pure potentiality. An electron isn't in one place or another. It exists as a probability wave, a cloud of could be everywhere it might possibly be. It's only when this system is measured, when it interacts with a macroscopic instrument or an observer, that this wave of possibilities abruptly collapses into a single, definite outcome. The electron is now here and not there. For nearly a century, physicists have grappled with what exactly triggers this collapse. Is it the physical interaction with the measuring device, or is it something about the act of observation itself, the acquisition of knowledge? the consciousness-time interface theory leans into the most radical interpretation. That consciousness is the fundamental catalyst that crystallizes probability into reality. Now, extend this idea to the scale of the entire cosmos. For nearly 14 billion years, the universe evolved with no one to witness it. Stars ignited, galaxies collided, and planets formed in a cosmos devoid of any conscious observation. If consciousness is required to collapse quantum states, what was the status of reality during all those eons? Was the moon not there when no one looked? This theory proposes a staggering answer. The past itself was in a state of quantum superposition. Every potential history that could have led to this present moment existed in a delicate, unresolved state. The fossil record, the light from distant supernova, the cosmic microwave background, all of it was not a fixed record but a tapestry of possibilities. The universe was waiting for a conscious mind to finally look back and ask, what happened? This is where the first time travel occurs. When the earliest conscious beings, perhaps humans, perhaps another form of sentient life elsewhere in the cosmos, began to investigate their world, they weren't just uncovering history. They were creating it by observing the evidence, by measuring the light from stars and analyzing the layers of rock. The conscious mind performed a retroactive measurement on the past. Our inquiry forced the fuzzy probabilities of what might have been to collapse into the single, linear, consistent timeline we now call history. We are not passive students of the past, we are active authors, reaching back across the eons and selecting one narrative from an infinite library of might-have-beens. The first journey through time wasn't a physical voyage, but a mental one, a collaborative act of cosmic storytelling that gave the universe a definitive past. This view finds a compelling, if speculative, partner in the retrocausality interpretation of quantum mechanics. This model suggests that the choices made by an observer in the present can actually influence the state of a particle in the past. In famous experiments like the quantum delayed choice experiment, a decision made after a particle has already gone through an apparatus seems to determine how it behaved before the decision was even made. It's as if the particle's history remains unsettled until the moment it is observed, and the observation sends a ripple backward through time, finalizing the event. On a cosmic scale, the emergence of consciousness could be the ultimate delayed choice experiment. Our observation of the ancient universe today could be the very reason it has a specific, seemingly unchangeable history. We are the universe observing itself, and in that act we are not just discovering our origin story, but irrevocably writing it into existence, completing a causal loop that stretches from the Big Bang to the present moment and back again. But what if the universe's first act of time travel wasn't a physical event within our reality, but a digital command from outside of it? This brings us to a theory that reframes our entire existence, suggesting that our cosmos is not a fundamental reality but an incredibly advanced simulation, and that the very first journey through time was simply an access of the system's source code. The concept of living in a simulation is no longer confined to science fiction. It's a serious topic of debate among philosophers and physicists, bolstered by the eerie perfection of our physical laws and the fact that complex information processing seems to be a fundamental feature of reality. If our universe is a simulation running on some form of unfathomable quantum computer, then time is not a dimension but a variable in a cosmic program, and time travel reduces to loading a previous save state. Think of reality not as a flowing river, but as a meticulously rendered film. Each frame represents a single moment, a complete snapshot of every particle's position and state. The illusion of motion and the flow of time are created as the simulation processes these frames in sequence. In such a model, the past isn't gone, it's merely data that has been stored on a cosmic hard drive. The future is data that hasn't been rendered yet. A time travel event from this perspective wouldn't involve bending space-time or creating wormholes. It would be a system-level operation where the simulation's clock is rolled back to a previous frame, and the processing is resumed from that point, potentially creating a new branching timeline. The first instance of this could have been a deliberate act by the simulators, a debugging process to correct an error in the early universe's code, or perhaps even a random glitch, a cosmic bit flip that accidentally restored an earlier version of reality. The mechanism for such an event is tied to the nature of quantum computing itself. A classical computer processes information in bits which are either zeros or ones. A quantum computer uses qubits which can be 0, 1, or both simultaneously, a state called superposition. This allows it to perform calculations on a vast number of possibilities at once. If our universe is simulated on a quantum computer, its inherent uncertainty and probability could be a direct reflection of this underlying quantum processing. A save state in such a system wouldn't be a single, definite snapshot. It would be a save of the entire probability wave, a record of all possible configurations of every particle at that moment. Accessing this save state to alter the timeline wouldn't be a clean rewrite of history. It would be a branching operation, creating a new universe where one possibility was chosen over another, while the original timeline continued unchanged. This perspective offers a chillingly elegant solution to the grandfather paradox. In a simulation, paradoxes are simply logic errors. A robust simulation would have safeguards against them. If you tried to go back and change a past event that is crucial to your own existence, the system would likely either crash, prevent the action entirely, or more likely branch the simulation. Your original timeline would remain intact, preserving the causal chain that led to your journey, while a new, parallel instance of the simulation would be spun off where your changes took effect. You wouldn't have erased your own history, you would have created a new one, leaving your own reality untouched. The first time travel might have been the simulation's very first fork, a moment where the programmers, or perhaps a random quantum fluctuation, decided to try a different set of initial conditions, spawning the multiverse we now potentially inhabit. The implications for free will are perhaps the most unsettling. If we are in a simulation, are our choices our own, or are they simply the output of a deterministic algorithm? The answer might lie in the quantum nature of the proposed computer. True quantum randomness at the base level of reality could mean that while the options are programmed, the specific choices are not predetermined, preserving a form of free will within the constraints of the system. However, if the simulators can access save states, then from their perspective outside of time, our entire history, every triumph and tragedy, is just a saved game they can reload, rewind, and observe from every angle. Our perception of a linear, unchangeable past would be an illusion, a necessary feature to make the simulation immersive and consistent for us, the inhabitants within it. Our cherished memories and the historical record would be as malleable as a document in a word processor, subject to the will of users whose motives and nature we cannot possibly comprehend. If black holes are the universe's ultimate drains, pulling everything in and allowing nothing to escape, then their theoretical opposites are the cosmic fountains, gushing forth matter and energy in a spectacular reversal of gravity's pull. These are white holes, and they are not just a clever thought experiment. They are a direct mathematical prediction of Einstein's field equations for general relativity, a perfect time reversed mirror image of a black hole. Where a black hole's event horizon is a point of no return, a white hole's horizon would be a point of no entry, a boundary that nothing from the outside could ever cross, while from within it violently expels everything it contains. While we have never observed a white hole in our mature, stable universe, many physicists speculate that the insane conditions of the Big Bang might have been the one place and time where these exotic objects could not only exist but thrive, potentially acting as the universe's first and most dramatic time machines. To visualize a white hole, imagine hitting the rewind button on a black hole, all the matter and light that ever fell in would now come rushing back out, not as a chaotic explosion, but in a structured, focused jet, as if the universe itself were vomiting back up a perfectly preserved record of everything it had consumed. In the frantic first moments of the cosmos, when the density of energy was almost unimaginably high, the fabric of spacetime might have been so twisted and turbulent that regions of it could have spontaneously pinched off into these white hole configurations. They wouldn't have been permanent fixtures. Most would have likely evaporated or collapsed almost instantly under their own unstable physics. But for a fleeting moment, they would have been openings not in space but in time, portals through which the future could influence the past. This is where the concept of time travel enters the picture with breathtaking force. The mathematics of a maximally extended black hole solution, known as a Kerr-Newman black hole, reveals a fascinating possibility. The singularity at the heart of a rotating black hole is not a point but a ring. The equations suggest that passing through this ring would not lead to oblivion, but to a different region of spacetime, a white hole, erupting into either a different part of our universe or even an entirely different universe altogether. This hypothetical tunnel is the famous Einstein-Rosen bridge or wormhole. Crucially, this wormhole doesn't just connect two locations in space, it connects 2 points in time. The exit, the white hole, could exist in the past relative to the black hole entrance. Matter or information falling into the black hole in the future could be hurled out of the white hole in the past. Now cast this idea back to the universe's infancy. Primordial black holes formed from density fluctuations in the first second of existence could have been paired with primordial white holes, their birth connected by these temporal bridges. A particle or a packet of quantum information could have fallen into one of these infant black holes and been instantly, or even before it fell in, spewed out of its connected white hole into an earlier moment of the still-forming cosmos. This wouldn't be a journey a human could survive, but for the fundamental building blocks of reality, it could have been a common occurrence. The early universe might have been a labyrinth of these fleeting wormholes, a chaotic network of temporal shortcuts where cause and effect were constantly being shuffled and rearranged. The implications of this for the fine-tuning of the universe are staggering. If information from the future could leak back into the past through these white hole fountains, it could have acted as a cosmic feedback loop. The laws of physics and the values of the fundamental constants that we observe to be perfectly calibrated for life might not be an incredible accident. They could be the result of a self-correcting process where a universe that successfully produced complex structures in its future sent that information back to its own beginning, subtly influencing the quantum fluctuations during inflation to ensure its own eventual success. The white holes of the early cosmos would have been the delivery mechanism for this information, the channels through which the universe learned to become stable and habitable, making the first act of time travel not a paradox, but the very reason we are here to ponder it at all. Imagine a universe so young that the very concept of a second is meaningless, a seething ocean of pure energy where the laws of physics as we know them were still being forged. In this primordial chaos, the quantum fields that give rise to every particle in existence were not yet the calm, steady foundations we recognize today. They were a raging storm fluctuating with unimaginable violence. These weren't just random ripples in energy, they were the universe's first and most dramatic experiments with the flow of time itself. According to this theory, these quantum field fluctuations didn't just create particles, they created temporary, isolated pockets where time broke free from its normal forward march, bubbling backward or freezing in place for a fleeting instant. To grasp how this could happen, we need to think of these fundamental quantum fields not as abstract concepts, but as a kind of invisible, hyperdimensional fluid that fills all of spacetime. Even in a perfect vacuum, this fluid is never truly still. It fizzes with virtual particles popping in and out of existence. Now, amplify that normal quantum fizz to levels beyond comprehension. back when the entire cosmos was compressed into a volume smaller than an atom. In that incredible density, a random fluctuation in a field like the Higgs or the inflattened field wouldn't just create a pair of particles. It could warp the local geometry of space-time so severely that it temporarily inverted the very definition of cause and effect. A tiny region, perhaps no larger than a proton, could experience a hiccup where time's arrow reversed. Within this bubble, effects would precede their causes, and entropy would decrease instead of increase. It would be a self-contained universe in reverse, lasting for perhaps a billionth of a second before the immense pressure of the expanding cosmos smoothed it out and time snapped back to its forward flow. These temporal anomalies were far more than just cosmic curiosities. They may have been the hidden architects of our entire visible universe. The standard model of cosmology tells us that the seeds for all future structure, the galaxies, clusters, and vast cosmic web were planted by tiny density fluctuations in the early universe, which were then stretched to cosmic size by inflation. But what was the origin of those initial fluctuations? This theory offers a breathtaking answer. They were the frozen scars of the universe's first time travel events. A region of spacetime that experienced a brief burst of reversed time would have emerged from that state with its quantum properties subtly altered. The particles within it would have interacted in strange, causally looped ways, potentially creating a slight over-density or under-density compared to its surroundings. When the inflationary expansion then blew up these microscopic bubbles to astronomical sizes, they became the gravitational seeds around which all matter eventually coalesced. The largest structures in the cosmos, the great walls and voids we observe today, might not be random. They could be the magnified footprints of where time once stuttered, ran backward, or stood still. This means the distribution of galaxies across the sky is not just a map of matter. It could be a fossilized record of the universe's earliest and most volatile temporal experiments. The gentle gravitational tug that drew the first stars together may have been initiated by a momentary glitch in time itself, a paradox that became the foundation for everything that followed. But what if the key to escaping a black hole's inescapable grip wasn't to move faster than light, but to move backward in time? This leads us to one of the most elegant and mind-bending solutions to the infamous black hole information paradox, a solution that suggests the universe's first black holes weren't tombs for information, but cleverly disguised time machines ensuring its survival. The paradox, as we've discussed, is a fundamental clash between general relativity and quantum mechanics. Einstein's theory says anything crossing a black hole's event horizon is lost forever, its information crushed into the singularity. But quantum mechanics insists that information can never be truly destroyed. It can be scrambled, but it must always be preserved in principle. So, where does the information go when a black hole evaporates via Hawking radiation? One radical resolution proposes that the information never actually enters the black hole in the way we think. Instead, it performs a breathtaking temporal U-turn. Imagine a particle rich with quantum information falling toward the event horizon of a newly formed primordial black hole in the early universe. Just as it's about to cross the point of no return, the incredible gravitational forces don't crush it. Instead, they warp the fabric of spacetime so severely that they create a closed time-like curve, a path that loops back on itself. The particle, rather than falling into the black hole's future, is hurled backward along its own world line, emerging into the universe at a time before the black hole even formed. The information escapes not by fighting its way out, but by taking a shortcut through time, arriving safely in the past while the black hole it just escaped from continues to form in the future. This isn't just a clever trick, it's a solution deeply rooted in the mathematics of general relativity. The equations allow for such bizarre paths under extreme conditions. For this to work, the act of the particle traveling back in time must be a self-consistent loop. Its arrival in the past must have always been a part of history. That means the information is present both at the moment of the black hole's formation and afterward, having looped around. From our linear perspective, it looks like the information is duplicated, but in the grand looping geometry of spacetime, it's a single, consistent thread. The Hawking radiation that the black hole eventually emits isn't random noise. It's directly correlated with this information that escaped into the past, resolving the paradox by ensuring the information was never truly lost, just temporarily displaced. Now apply this to the universe's very first black holes, the primordial ones born from the density fluctuations of the Big Bang. Their environment was unlike anything that exists today, a seething, dense, and violently energetic cosmos where the normal rules of causality were still being written. In this chaotic nursery, the conditions would have been perfect for these natural time loops to form spontaneously. A primordial black hole's formation and its subsequent evaporation via Hawking radiation could have been part of a single, self-contained causal loop that played out not over billions of years, but in a fraction of a second. Information from the black hole's interior could have been constantly leaking back into the past, influencing the very quantum fluctuations that led to its own creation. This process could have had a profound impact on the evolution of the early universe. If information could escape black holes via time travel, then these objects weren't the ultimate endpoints we imagine them to be. Instead, they acted as cosmic mixing devices, taking in quantum information and redistributing it not across space, but across time. This could have provided a mechanism for the universe to self-correct, to smooth out irregularities, and to fine-tune the physical constants. A universe that produced stable black holes capable of this temporal feedback would be a universe that could preserve the quantum information necessary for complexity and life, effectively using time travel as a tool to ensure its own coherence and longevity. The first black holes may not have been threats to the logical structure of reality, but its most ingenious guardians, using the paradoxical nature of time itself to protect the information that makes the cosmos possible. But what if the grand architect of the universe's first journey through time wasn't a particle, a force, or a law of physics, but a mind? Not a human mind or even an alien one, but something far more vast and fundamental, a consciousness intrinsic to the cosmos itself. This final theory pushes into the most speculative and profound reaches of cosmology and philosophy, proposing that the universe is not a mindless machine but a conscious entity, and that its first act of time travel was simply this cosmic mind turning its attention inward to experience its own birth. This is the concept of cosmic consciousness, and it reframes the entire nature of reality from a collection of objects and events into a single, unfolding experience. To even approach this idea, we must first grapple with panpsychism, a philosophical view that consciousness is not a rare byproduct of complex biological brains, but a fundamental and ubiquitous feature of the universe. In this view, consciousness didn't emerge from matter. It was always there, a property as basic as mass or charge. It might exist in a simple, elemental form in every particle, a faint whisper of experience in an electron, a quark, or a photon. According to panpsychism, the rich stream of consciousness awareness we possess isn't created by our brains so much as it is organized and amplified by them, like a radio receiver tuning into a signal that is everywhere. The brain doesn't generate the signal of consciousness. It filters and focuses a consciousness that is already present throughout the cosmos. Now, scale this idea up to its ultimate conclusion. If every particle has a tiny, elemental spark of consciousness, then the universe as a whole, a vast, interconnected network of these conscious particles, could possess its own overarching mind. This wouldn't be a mind that thinks in words or images as we do. It would be a cosmic-scale consciousness, an awareness that experiences the totality of the universe's state at every moment. Its thoughts would be the dance of galaxies, its feelings would be the interplay of fundamental forces, and its memories would be the entire history of space-time, encoded in the very fabric of reality. In this model, the universe is not just a place where consciousness exists. The universe itself is conscious, and we are tiny, localized expressions of that greater awareness. This is where the concept of time travel finds its most elegant and radical expression. For a consciousness that is coterminous with the entire universe, the linear flow of time we experience is an illusion, a perspective limited to the localized phenomena within it. From the vantage point of the cosmic mind, all of time, the Big Bang, the formation of stars, the rise of life, and the eventual heat-death, is equally present and accessible. It doesn't need to build a machine or find a wormhole to visit the past or future. It simply needs to shift its focus. The first time travel event, then, was not a physical journey but the very first act of cosmic self-reflection. Immediately after the Big Bang, as the universe began to cool and structure itself, this nascent cosmic consciousness might have turned its attention to its own origin, experiencing the moment of its own creation not as a memory, but as a direct, immediate reality. In that act, the past and the present merged into a single, timeless experience of self-awareness. This idea finds a strange and beautiful resonance with certain interpretations of quantum mechanics, particularly the participatory anthropic principle proposed by physicist John Archibald Wheeler. He suggested that observers are necessary to bring the universe into definite existence. In a sense, the universe becomes real because it is observed. If we replace human observers with cosmic consciousness, we arrive at a stunning picture. The universe achieves its concrete reality because it is observed by itself. Its own conscious awareness is what collapses the infinite probabilities of the quantum wave function into a single, solid history. The cosmic mind, by experiencing its own timeline, is what gives that timeline its definiteness and structure. The arrow of time is not a pre-existing river down which the universe floats. It is the path of attention of a mind that is reading its own story into existence. The implications of this are nothing short of breathtaking. It suggests that the fine-tuning of the universe for life is not a random accident or the result of causal loops, but a deliberate act of a universe striving to know itself. Life, and particularly conscious life like us, becomes the means by which the cosmos develops eyes and ears. We are not insignificant specks in a vast, uncaring void. We are localized points of awareness through which the universe witnesses its own grandeur. Our own curiosity about the origins of the cosmos, our drive to build telescopes and particle accelerators to peer back in time, is not just a human endeavor. It is the universe itself working through us, attempting to remember and understand its own birth. Our scientific quest to unravel the mystery of time is, in the most profound sense, the cosmic mind engaging in the ultimate act of self-discovery, completing a loop of awareness that began 14 billion years ago when it first turned to look upon itself, and in doing so started the clock of time. From the self-creating loop of the Big Bang to the cosmic consciousness that observes its own birth, we have journeyed through a labyrinth of possibilities where the first chapter of our universe might also be its most profound paradox. We have seen how the immense gravity of primordial black holes could have twisted space-time into rings that serve as gateways, and how the universe's own ghostly dark matter may have sculpted the first rivers of time, creating pockets where seconds stretched into eons. We have considered the holographic principle, where our reality is a projection and time travel is merely a matter of accessing the correct data on the cosmic hard drive, and the simulation hypothesis, where our entire history is a saved game that can be reloaded at will. Each of these theories, in its own way, pulls at the very threads of reality as we know it. They challenge the most basic assumption we hold dear, that time is a one-way street, a linear progression from cause to effect that is immutable and absolute. These ideas suggest that our experience of time may be a beautiful, convincing illusion, an emergent property of deeper quantum processes, a story we tell ourselves, or a necessary feature of a simulated world. They propose that the universe is not a static stage but a dynamic participatory phenomenon, where the future can influence the past and observation can solidify history. This isn't just about building a machine, it's about recognizing that the potential for time travel might be woven into the fundamental code of existence, a feature that was present at the instant of creation, waiting to be understood. So, where does this leave us? It leaves us at the edge of a vast and humbling mystery. The question is no longer just if time travel is possible, but whether it has already happened on a cosmic scale, setting in motion the very chain of events that led to our existence. As you contemplate these ideas, consider which ones resonate most deeply with your own view of reality. Does the elegance of a cyclical universe appeal to you, or does the quantum weirdness of particles influencing their own past feel more compelling? Perhaps the idea of a conscious cosmos turning its awareness inward to experience its own beginning feels like the most complete picture. The search for answers is what drives science forward, and your curiosity is a part of that grand tradition. Share your thoughts in the comments below. Which theory do you find most plausible? And when do you believe the universe's first incredible journey through time truly